Java virtual machine, we call it as JVM, which analyzes the bytecode, interprets the code, and executes it. It is very important as a developer that we should know the architecture of the JVM, as it enables us to write code more efficiently. In this session, we will learn more deeply about the JVM architecture in Java and the different components of the JVM. First, what is a JVM? A JVM is a virtual machine. Is a software implementation of a physical machine. Java was developed with the concept of write once, run anywhere, which runs on a virtual machine. The compiler compiles the Java file into a java.class file. Then that .class file is input into the JVM, which loads and executes the class file. Let's take one example. I already write down code. This is that one. Hello world.java, and this is the class thing. We are going to save this one with the extension of .java and try to compile this one. And the compilation process is, I already explained how to compile. One more I want to explain that one. When we are going to compile, first we have to call the compiler. So by using the Java C, we will done that one. And next, class name. Class name or case sensitive. So you have to enter appropriate class name which you are given class name and file name. Here we have something. I already compiled this one, that's why it's showing you have a class file there. So I'm going to delete my old one. Yes. After compilation process, one class file is created here. So here the compiler converts the .java file into the .class file. Then the .class file is this .class file is input into the JVM. So the JVM works on this .class file, and let's execute this one. See, it executed. Hello world. So the JVM will work on a .class file, and this is the JVM architecture. In the JVM architecture, we have three steps: class loader subsystem, runtime data areas, execution engine, mainly. Okay, so in the first component is a class loader subsystem. So how does the JVM will work? The class loader subsystem works like Java's dynamic class loading functionality is handled by the class loader subsystem. It loads, links, and initializes the class files when it refers to a class for the first time at runtime compile time, because it works on that class file, so the compiler process is already done after the work what compiler does. Like .java file is converted into the .class file by the compiler. So the JVM works on .class file. That .class file is entered into the class loader subsystem. So this functionality is done in dynamic way. Classes will be loaded by this component, and here we have a loading diagram. In that we have three loaders. First one is bootstrap class loader, second one is extension class loader, third one is application class loader. First one, bootstrap class loader, responsible for loading classes from the bootstrap class form, nothing but rt.jar. Highest priority will be given to this loader, and we have a rt.jar in Java folder where it's installed in C drive or D drive, yes, whatever maybe, where we install the Java software. There we have a rt.jar. By using that one, by using that class path, it will work. And the second one is extension class loader, responsible for loading classes which are inside uh, ext folder, JRURL folder. Third one is application class loader. It's responsible for loading application level class path mentioned environment variable. For example, if we have a JBoss or WebSphere or a Tomcat, so we have to give one class path for that. According to that class path, it will work. The above class loader, which follow delegation hierarchy algorithm, will loading the class files. And this is the linking process in a class loader subsystem. There we have three stages: verify, prepare, and resolve. Verify. The bytecode verifier will verify whether the generated bytecode is proper or not. If verification fails, we will get the verification error. For example, um, first the Java file is converted into the machine language and stored with the .class extension that call it as a bytecode. That bytecode is verified by the JVM verifier. If any problem is there, we call it as a runtime errors. We will explain the errors in our future sessions. So those runtime errors are verified by a verifier and displayed. So it verifies whether the bytecode is okay or not. If it fails, it shows some verification errors. And the second one is prepare. For all static variables, memory will be allocated and assigned with default values. So all the static values are allocated with the default value. If we doesn't initialize the static variable, automatically it will done that one. And the third one is resolve. All symbolic memory references are replaced with the original references from method area. This is the method area, and this resolve is done. Symbolic memory references are replaced with the original references by taking input from method area. And third one in class loader subsystem is initialization. This is the final phase of class loading. Here all static variables will be assigned with the original values and the static block will be executed. Earlier, static variables are allocated with the default value. If it doesn't given any value, it's done in a prepare. And the same thing is done here also, but with original value, which we are initialize that one. And the second component is runtime data areas. The runtime data area is divided into five major components. The first component is method area, second component is heap area, third one is stack area, fourth one is PC registers, fifth one is native method stack. First one, method area. All the class level data will be stored here. All the class level data will be stored here, static variables include. There is only one method area per JVM, and it will share reserve. All the method level, all the class level, which will like instance variables, stack variables are stored here. We will explain in instance variables, static variables, and future sessions. Second one is heap area. All the objects and their corresponding instance variables and arrays will be stored here. There is also one heap area per JVM. Since the method and heap area share memory for multiple threads, the data stored is not thread safe. Actually, any thread can access the heap area methods or heap area objects which are stored in that one. And third component is stack area. For every thread, a separate runtime stack will be created. For every method call, one entry will be made in the stack memory, which is called as stack frame. All local variables will be created in the stack memory. The stack area is thread safe since it is not a shared resource. The stack frame is divided into three subcategories. Local variable array related to method, how many local variables are involved in the corresponding values will be stored here. Operand stack, if any intermediate operation is required to perform operand stack act as runtime workspace to perform the operation. Frame data, all symbols corresponding to the method is stored here. In the case of any exception, the catch block information will be maintained in the frame data. Let's say I would like to draw stack diagram for you. Let's take these are the three blocks we have in Java stack. First one is local variable array related to the method, how many local variables are involved and the corresponding value will be stored here. And the second one is operand stack, if any intermediate operation is required to perform operand stack act as a runtime workspace to perform the operation. Frame data, third one, all symbols corresponding to the method is stored here. In the case of any exception, the catch block information will be maintained in the frame data. Basically, when a method is called or invoked by the main method, and the main method is placed here, and it calls any another method, it will pick up and append to the main method. Actually, this is the top at the top of the method which is invoked by the main method, that is top on main method. That will explain in next sessions about Java stack totally. And the next one is yeah, the next one is PC registers. Each thread will have separate PC registers to hold the address of current executing instruction. Once the instruction is executed, the PC register will be updated with the next instruction. So it counts the instruction execution of instructions. The fifth one is native method stack. Native method stack holds native method information. For every thread, a separate native method stack will be created. Execution engine. This one is the execution engine. The bytecode which is assigned to the runtime data area will be executed by the execution engine. The execution engine reads the bytecode and executes it piece by piece. In that we have two two compilers or two main blocks. First one is interpreter. The interpreter interprets the bytecode faster but executes slowly. The disadvantage of the interpreter is that when one method is called multiple times, every time a new interpretation is required. This is the advantage with the interpreter. So they are designed one more one that's JIT compiler. The JIT compiler means just in time compiler. It neutralizes the disadvantage of the interpreter. The execution engine will be using the help of the interpreter in covering bytecode, not covering, converting bytecode. But when it finds repeated code, it uses the Java in-time compiler, which compiles the entire bytecode and changes it to native code. This native code will be used directly for repeated method calls, which improve the performance of the system. Then we have in the JIT compiler we have three more steps. First one is intermediate code generator. Intermediate code generator produces intermediate code optimizer responsible for optimizing the intermediate code generated above. Target code generator responsible for generating machine code or native code. And the fourth one is profiler. This one is the extra block which we have in zip compiler, a special component responsible for finding hotspot, that is whether the method is called multiple times or not. And next one, in the execution section we have a zip garbage collector. In earlier session we discussed about automatic deallocation. The programmer is responsible for allocation of memory, that's it, and the deallocation will be done by the garbage collector, which is in JVM. So that's the and this one is the garbage collector in the execution engine. Collects and removes unreferenced objects. Garbage collection can be triggered by calling system.gc. This is the command to call garbage collector. System.gc. This one is a command for calling the garbage collector, but the execution is not guaranteed. Garbage collection of JVM, the objects that are created. Basically, the garbage collector done its work automatically after closing or after completion of the complete execution of a class. So we no need to call separately uh, to the location memory, or we no need to call garbage collector. Java native interface. This is the native interface. We call it as a J and I. Will be interacting with the native method libraries and provides the native libraries required for the execution engine. Basically, I didn't explain the native interface, right? So, what is the native interface means? The code which is not related to the Java, or the code which is not Java code. Those methods, those classes, those information we call it as a native information. So we need some interface to interact or to combine the Java code and the native code. That purpose we have this one, Java native interface. This Java native interface will be interacting with the native method libraries and provides the native libraries required for the execution engine. And the fifth one is native method libraries. It is a collection of native libraries which is required for the execution engine, and this is the JVM architecture and how JVM works. So this is the main topic which we have in Java. So friends, if you like this one, please subscribe my channel by clicking on the subscribe button below in this icon, and give some comments to improve my communication skills and explanatory skills technologically and developing things. Thank you. Thanks for watching this video.